So my interest is in using period maps to understand moduli spaces. So today P will stand for a period map from some moduli space to a period domain. So to an algebraic variety smooth, you associate some cohomology group, the Hodge structure on some cohomology group. This is a classifying space. And the question that concerns me today is extensions to boundary. So ideally, you would want to have some sort of compactification on this side and go to some sort of compactification on the other side. So for instance, of interest is when, say, you have KSBA here. So this is a Kolar-Shepard-Baron compactification. This is a geometric compactification. And you would want to map to, say, like the Kato-Usui generalizations of toroidal compactifications. So you might say, so here we know, so you might say this is not an algebraic space, so it doesn't have an algebraic structure, but the truth is that in the directions coming from algebraic geometry in the horizontal directions, we have nice behavior at the boundary generalizing the toroidal compactification, so there is some hope to have such an extended period map, and there is some sort of zero-level evidence for something like this being reasonable. Is, for instance, the theorem of Kolar and Kovac on the fact that objects here are have Dubois singularity, so they behave well Hodge theoretically. So why would you want to do something like this? Is because you would want to establish, for instance, properness for period maps, appropriate properness results for periods, and you would want to establish things, so use structure on D by gamma to get structure on moduli. And as in Christian's talk, to do these kind of things, you have to move away from a normal crossing situation and so on. But this is kind of a talk in the future. So today I'll discuss something very classic. So we will go back to the classical situation. So specifically, the period domain will be just weight 1. So D mod gamma here will be just the AG. And the compactifications are toroidal compactifications. So we are considering toroidal compactifications of AG. Specifically, we consider either the second Voronoi compactification, the perfect cone compactification, or the central cone compactification. So here, if you know anything about toroidal compactifications, you know that there is a plethora of compactifications. Among those, for abelian varieties, there are 3 that stand out. The Voronoi is special because this is modular due to Mumford, Namikawa, and Alexeyev. This is the canonical compactification of AG for G large enough. This is Shepard-Baron. And this is, in some sense, the closest to Bailey-Borel, Satake-Bailey-Borel. So in some sense, those 3 compactifications are natural. So the question that will be of interest today is you have a moduli space such that the Hodge structure is of weight 1, and you want to extend it to one of these toroidal compactifications. The motivation, the concrete motivation for us is cubic threefolds. And I should say who are us. So this is joint with Casalena Martin. So this is, we have several papers on this, and what I'm talking today is also joint with Hulek and Gruszewski. Okay, so we are considering cubic hypersurfaces. I already used, so X in P4, a cubic And what is known by work of Griffiths and Clemens and Griffiths is that the intermediate Jacobian is a principally polarized abelian variety of dimension 5. So basically, one gets a period map from M to A5. Now I should note this is dimension 10, this is dimension 15. So the image would be high codimension. So we have Torelli and many other things. So the question that interests me is basically to understand the closure of the intermediate Jacobian locus. So if I call this one P, so this is P of M inside A5, maybe compactified and maybe closure here. So we have a theorem already a couple of years ago, so Casalena Martin and myself in 07, I think, which says the following. So it says that the boundary of the intermediate Jacobian locus in the Satake compactification, this is a Satake-Bailey-Borel compactification, consists of 3 divisors. So in other words, the closure of this locus in A5 is 3 irreducible components of dimension 9, and those 3 divisors, like the generic point, is described as follow. So this is C star extensions of Jacobians of genus 4, hyperelliptic of genus 5, and finally there is one exception, GC, so this is genus 4 with a unique G13 times the Jacobian of an elliptic curve. So this is the theorem. The Satake-Bailey-Borel compactification, and I should say, I mean, I will not take it down. So the last one is in the boundary of A5 star. The other ones are in the interior of the moduli space. So those are already in the interior. And kind of the key ingredients to this one, let me just, key ingredients here are 2. So first of all, we have a theorem. One direction is due to Mumford. The other direction is to Casalena Martin and Friedman, which says that if A is an intermediate Jacobian for a smooth cubic, if and only if the theta divisor has a unique triple point, maybe ordinary triple point or something like this. So you characterize the intermediate Jacobians in A5 by conditions on singularities on the theta divisor. And the second, so this is one key ingredient, and the second is basically we construct a normal crossing compactification of M bar of the moduli of cubics. And the idea here is very nice. The idea basically is you consider the GIT compactification. You have a rational map to A5 star. This is strictly rational, but then you can blow it up to normal crossing, and by Borel extension, this will give you a map here. And this normal crossing is constructing using the fact that M bar, here is a bit of lie. One has to be a bit careful here. This is a 10-dimensional ball quotient, and this is a result due to Alco-Casson and Toledo. So using a kind of an exotic period map, you obtain that the moduli of cubic fourfolds, the compactified version is a 10-dimensional ball quotient. In some sense, a new example. I mean, Deligne and Mostow have the examples of ball quotients of moduli being ball quotients up to dimension 9 coming from points on the line. This is a truly new example, a 10-dimensional example. And then using this kind of description and the geometry of the situation is kind of easy to produce a normal crossing, and this is kind of explicit. So meaning that to every point here you have some sort of geometric meaning, and then using the fact this is a map, you only need to understand what's happening to generic points of strata, and then it's kind of easy to prove that. There is a
simple picture when we consider minimal singular compactification.
Yeah, that's kind of what I was saying, and this is kind of the point of my talk. As soon as you have a normal crossing compactification, then you'll map to the Satake-Bailey-Borel. So this is the question, and the much more difficult question is try to lift. So basically the question is try to lift. So you have M tilde mapping to A5 star. All the toroidal compactifications dominate the Satake-Bailey-Borel, and you try to say, do I have an extension here? And this is what I will talk today. So the claim, this is Casalena Martin, Gruszewski, Hulek, and myself, which is 14 plus. So this is, we are pretty confident, but maybe let me call it just a claim. So indeed, M tilde extends to the Voronoi or the perfect cone, and as a corollary, one can compute the image of the period map, the boundary of the intermediate Jacobian locus. And I want to say what is involved in something like this, and to do a concrete example here. So let me kind of water down the problem. So let me go to prime varieties. So this is the content of my talk. The cubics were just motivation. So for, I mean, there is a close connection between cubic free folds and prime varieties, because the cubic free folds can be realized as conic bundles over P2, and there you automatically get an associated prime variety and so on. So basically, in some sense, you can say that the primes are even more general than cubics, but anyway. So what is a prime variety to start, and then what do we prove? So the prime varieties are just some natural generalization of the Jacobians. So one starts with an étale double cover. So this is étale double cover. And the prime variety associated to this situation is simply the kernel of the norm map going from the Jacobian of C to J of C, 0. So anyway, so this, so if the genus of this one is G plus 1, then this would be a principally polarized abelian variety of genus G. So one gets a map from Rg plus 1. This is the moduli space of primes, which is just a finite cover of Mg plus 1 into Ag. And the question is, so before getting to the question, let me note that Beauville constructed a normal crossing geometric compactification Rg plus 1 bar sitting over Mg plus 1 bar, and these are just admissible double covers. And I mean, so there is an entire definition that you can mostly make it up. So the key point, the admissible part, is at the fixed points. So obviously here you'll have again some sort of 2-to-1 map on the components, and the fixed points of this map are included in the nodes of C tilde. And if you have a fixed node, if a fixed node, then the admissible condition is that no interchanging of the branches. So you consider the obvious definition, but the point is that if you have a fixed node, you don't change the branches, the local branches there. And of course, as I said, by Borel extension, you automatically get an extension to the Satake. And the question that I want to address today is, can you lift it here where sigma is Voronoi, perfect, or central?
Sorry, I have a single question. Would you put dimension count on these quantity divisors? Like, the any component is like A4, so it's four-dimensional, so these divisors are nine-dimensional.
No. So you see, okay, so as I said, these are actually in the interior. So this is in the boundary. This is in the boundary of A5 star, and these are in the interior. So let me just do a dimension count. You see, so here, for instance, you have a Jacobian of a genus 4 curve. So genus 4 are 9 moduli, but you impose the condition that it has a single G1 free. That's a codimension 1 condition there, and then you get the elliptic curve, so it's 9-dimensional. And I mean, so I should say, maybe the more interesting thing is that this comes from cubics with A2 singularities. This is kind of the elliptic tail situation for people that know about this stuff. This comes from the chordal cubic. This is the secant to the rational normal curve. And this is kind of the vanilla one. This comes from the A1 cubics. So first of all, what is known? So let me say what is known in this situation. Because we are talking about prims, I should say first about Jacobians. So what do we know about the Jacobian map? So mg bar Deligne-Mumford to ag sigma, where sigma again is like that. So first of all, we have Mumford. This was like before 80s probably. So we have an extension mg bar to ag Voronoi. Kind of surprisingly, it took, I don't know, maybe 30 years or so, when we only recently have Alexeyev Bruniat, I think 2012, where they proved the following things. So one is that you have an extension to the perfect cone compactification, and two, you have there doesn't exist an extension to the central cone for G large enough. I think G larger equal than 9.
Could you please say a word why before you prove, why do you expect it to result? What's the difference between perfect and?
Actually, you'll see when I state, I mean, so kind of our goal, I mean, so in some sense, I mean, our goal and our paper, kind of the main thing that I think, from my perspective, it achieves, it makes these kind of results transparent. It makes clear what's going on, and kind of to make this type of results kind of systematic. For curves, you are always misled, because kind of for curves, you have all kind of the geometry of curves and so on. And we wanted to do it for cubic freefolds in a kind of in a systematic way and so on. And this is kind of our goal, and you'll see later on what's going on. And there is actually kind of, now this is a trivial corollary nowadays. But you see that it took a long time to realize this, and you'll see later on. Anyway, and I mean, so this one is kind of the one that you kind of expect, because this is modular. And this is kind of modular, so if there is justice in the world, you expect that modular for curves is kind of compatible with modular for abelian varieties and so on. But kind of the surprise is that for prims, this is a theorem of Friedman and Smith, Roy Smith. The fact is that there is, so Rg plus 1 bar does not extend to any of these Ag sigma. So the question is, indeterminacy locus, resolution, and maybe why this, what's going on. So in the sense of sorry, no, the Voronoi, the second Voronoi, and here again you have, so you have this this modular compactification due to, I mean, initially Mumford and so on, and Alexeyev give a functorial meaning. Yes, so this is obtained. The idea is to start with A theta and to see it as stable pair in the sense of Kolar-Shepard-Baron. And then, I mean, so here you'll have multiple components, so you need to take the main component and stuff like that, but that's the meaning. Okay. So as I said, there is actually not a good extension, and actually we have these kind of Friedman-Smith examples, which are kind of very simple. They look like, okay, so it's kind of, let me just draw it this way. So this is a curve C tilde mapping to C. You have an involution on C tilde going to C tilde. So I of the components, so C tilde is two components, C1 union C2. The two components are preserved, and the nodes are pairwise interchanged. So you have I of the node P2I minus 1 is P of 2I, P1, P2, and so on. Or if you want to do the dual graph, that we'll do a lot later on, it looks like this one. So this is the dual graph, and you interchange pairwise. And this would be called Friedman-Smith N. So there are two N nodes. So the N stands for like codimension in the moduli, because N is the number of nodes for C, which is really what matters in terms of moduli. And the kind of, so Friedman-Smith example was in the 80s, and the more recent result was Alexeyev, Birkenake, Hulek, maybe 2002 or something like this, so about 10 years ago, which they proved that the indeterminacy of the prim map to the Voronoi, this is precisely the union of the closures of Friedman-Smith loci. Okay, so let's go and see what's going on and what's involved in extending toroidal compactification. So let me start with some generalities. So first of all, about toroidal compactifications. This is just a bird's eye view, I mean, mostly to fix the notation to what I mean, so toroidal compactification. So the toroidal compactifications are refinements of the Satake-Bailey-Borel, which in the case of AG is just AG minus. Yes.
So if you just look at the
No, no, no. To the Satake is defined because it's normal crossing compactification. So that's the question. So everything is kind of lifting to the yeah. Okay, so here you have the toroidal compactifications that are very the Satake compactification, and what is involved here. So in terms of limit mixed source structure, so here to give a boundary component in Satake-Bailey-Borel, it simply means you fix an isotropic subspace, totally isotropic. So this is a totally isotropic subspace, and this is V, which gives you the AG, where the variation of Hodge structure lives. Once you have a totally isotropic, of course, you really get a filtration, -1 equals 0, W0, W1 is W0 perp, and then W2 is V. And basically, the Satake-Bailey-Borel simply encodes the Hodge structure on W1 minus modulo W0 on the graded piece 1. So the toroidal compactification encodes the extension data. So the toroidal compactification lives over the Bailey-Borel compactification. So you already have this piece, like the continuous varying piece, so the weight 1 piece. So the toroidal compactification basically encodes the extension data for the limit mixed Hodge structure. And basically it involves a choice. So you are choosing this kind of sigma is an admissible decomposition. So if you are sitting over the boundary A mu, then you have, this is an admissible decomposition of the cone of G minus mu times G minus mu symmetric imaginary positive definite matrices. So this is the standard. So you have the cone. These are G minus mu times G minus mu matrices. So this is kind of the extension data in some sense. And you have a rational polyhedral decomposition sigma of this cone. So the only thing that I want to note here is that, so when you write it in this way, is kind of not intrinsic. So the intrinsic way to say this cone lives, the cone lives, this is a point that's kind of key, it lives in sim2 of GR2 of W dual. I mean, this is kind of standard, but you'll see. So I mean, everyone knows, I don't know, to give the Bailey-Borel compactification, you do that, and over it you take rational polyhedral decomposition of this, but it's important from a Hodge theoretic perspective to identify that in some sense canonically what you are doing, and the cone that you are considering, you are considering basically the positive cone in this. Yeah. So I'm saying once you fix the Bailey-Borel, you are fixing the filtration. And of course, kind of for filtration in the abelian variety sense, you only have like the dimension. So it's just a number essentially, but kind of intrinsically, that's what you are doing. On the other hand, you have like the geometric context. So we know by Catani, Delin, Kaplan, what is and Schmidt in the one-dimensional case, what's kind of the behavior near the boundary for polydisks. Sorry?
Okay.
Okay.
But
Okay, Schmidt, anyway, it would be. Okay, so we know the behavior of the for polydisks, and this is what we are needing here. And I mean, so in our situation, I mean, we really care about like how to say, we only care about the discrete behavior. So basically, our moduli space is a polydisk near the boundary. And it looks like this, and you have monodromy transformation. These are log of Ti corresponding to the various things. And you are considering the key ingredient here is the monodromy cone. Let me denote it like this. So this is the monodromy cone. So this is like a boundary point. And this is the span of the R plus span of the monodromies. And this is, as I said, you should view this one as living in SIM2 GR2W dual. And by general toroidal, so by general toroidal stuff, you know that the period map extends at C tilde mod C if and only if this monodromy cone is contained. So there exists a cone sigma belonging to the toroidal data such that this monodromy cone, so this is a monodromy cone, this is a cone coming from toroidal choice, that you have such an inclusion. That's the statement. And I mean, so this is completely general. And so what did we do, and kind of what's the content? So what is our content? So the first one, we have to explain the computation of the monodromy cone in terms of geometric data, of the geometry of C tilde mod C. And second of all is to kind of fit this with the combinatorics of sigma. And I mean, so kind of part of, I mean, so even if you read for Jacobians, and this was a big issue, I mean, when you try to understand the papers on Jacobians and so on, is that these kind of steps are all messed around and mixed up and so on. So it's important to kind of separate the things. So now, of course, what do we know about the monodromy? So we know like monodromy in this kind of trivial situation is generated by is given by Picard-Lefschetz. So that's one thing that we know. And the second thing that we know is that kind of everything in weight 0, or kind of in this situation, this is some sort of duality, weight 2 is controlled by the dual graph. By the dual graphs. Yeah, I mean, yes. So you'll see what's like the Picard-Lefschetz for prims. What's kind of the corresponding Picard-Lefschetz for prim. So that's.
Yeah.
But what I'm saying, so what is Picard-Lefschetz? What do I understand by Picard-Lefschetz? So I'm treating kind of like both the Jacobians and Prim in the same. So Picard-Lefschetz gives us the monodromy around the node, monodromy for a node. You'll see. Just bear with me like a minute. So here in this situation, the situation is a bit more complicated, of course, and even dual graphs. You have two dual graphs. So you have the dual graph of C tilde, and you have the dual graph of C. Now the admissible condition tells you that you actually have an induced involution here. So this is the admissible condition. So in fact, you have some sort of covering map there in terms of dual graphs. And the two key claims are, let me just put them there and then explain. Okay, so for Jacobians, we have canonical identification between GR2 of W. This is kind of the limit mixed Hodge structure, and H lower 1 of gamma. And recall that the monodromy lives in our world, lives in sim2 H1 gamma dual, which at least over Q is a quadratic form on H upper 1 gamma, and then Picard-Lefschetz in this situation. Lefschetz tells us that the monodromy corresponding going around the edge is simply E square dual. So you see that E is an edge, so you can see it as an element of C1. E dual would be an element of C upper 1, and you take the image in H1. So your monodromy transformation with this identification is simply E square, E dual square. This is just the standard Picard-Lefschetz formula. So for prims, we prove, and I mean, so it's not particularly difficult, is the GR2 part is H1 of gamma minus, so the anti-invariant part in H1, and then the monodromy transformation can be identified with E tilde dual minus the E tilde dual to the square. So this is monodromy for going around the edge in gamma. Because remember, let me just recall, so the divisor, so this is like the boundary of Rg plus 1. Locally, these divisors are indexed by E in the edges of the dual graph of gamma, so by the nodes of C. Now, if you have an edge here, you can take a lift upstairs in the dual graph of gamma tilde. And now you have typically two choices, and you take the difference. But in fact, because you are taking the square, is kind of independent of that. Sorry? No, so I'm taking the generators of C upper 1 are the duals. So this is our notation. So this is, and then I'm just taking the image. Not the image can be 0, for instance. So it can happen that the image is 0. So the thing that, I don't know, do you see an issue here? Kind of what's kind of the main thing here? I don't know if you, I mean, in some sense, these are kind of, I mean, this is not hard. I mean, the thing that took us a while to understand is, if you try to write this like Picard-Lefschetz transformation, if you write the Picard-Lefschetz transformation, this kind of lives on a one-dimensional space, in some sense. So this corresponds, I mean, kind of like going around just an edge. This is a C star and so on. And what's going on is that, you have natural maps. So if you have, let me do it in the case of curves. So if you have C and you have a partial smoothing, then you have a dual graph here. Then you are simply collapsing the edges corresponding to the smooth node. And then you get a new dual graph here. And it turns out that you have natural maps. H1 gamma, I think, goes in this direction. Let me check my notes. Which are compatible. Okay, let's pretend that this is the case, if not the other way around. But I think this is the correct thing, which are compatible with the identification with GR2. And this is something to prove, because kind of the identification to GR2, this is via Clement-Schmidt exact sequent. This is something purely combinatoric, and you need to prove that the topology of partial smoothings actually respects this. Once you get this one, basically this rank 1 matrix, and this is kind of the key point. Note that this is a rank 1 matrix. And basically, you are lifting it. Obviously, it will be still rank 1 to like a G minus mu times G minus mu matrix. That's kind of the key point here. Because kind of the point is how all these kind of edges fit together and so on. And once you do that, then you understand everything. And finally, the final piece of notation. So notation, this is for E in E of gamma, I denote L of E. This would be an element in H1 gamma tilde minus, which is by definition, this is either E tilde minus I E tilde or 1/2 E tilde minus E tilde. This is basically the primitive generator. So this would be the case if there should be duals here, duals. If E tilde dual is equal to minus E tilde dual in H1. So this is kind of the monodromy would be given N of phi. I mean, the monodromy, the way it's defined, is only over Q, so you don't really care. So the monodromy would be defined L E square, but it's actually important to take like this primitive generator. So let me put let me put the main results now. So we are considering C tilde mod C a boundary point in Rg plus 1. And the statement is the period map extends here if, and we have the condition, so the Voronoi case. So in the Voronoi case is very simple. Basically, for any collection E1, EM of edges in the dual graph of C, such that LE1, LEM is a basis, is a Q basis of H1 gamma Q minus, then LE1 up to LEM is a Z basis of H1 gamma tilde Z minus. So you know that all these edges, so E1 up to E, if you take the entire collection, they will generate the H1 of H1 of what I wrote there. You are subtracting a collection such that you get a basis, and the condition is that this is actually a Z basis. For the perfect cone, yeah, so in that situation, it turns out, I mean, so it turns out that you get something very kind of like silly. You get something like this. So in that situation, I think LE1, you take LE1 to LE4. So let's say that you have the simplest case. And with natural basis of this one, then it turns out that the matrix you get is this one. So that has determinant 2. It's not a Z basis. I mean, so this one, and I mean, so I cannot explain it here. I mean, so that I mean, it's subtle because you have various things. You have anti-invariant cohomology, anti-invariant homology, and they are not actually dual. And that's actually what's measured. This is the invariant subspace, and I don't remember exactly. I think it would be maybe included in the or anyway, yeah. Okay, and for the perfect cone is a condition. So there exists Q, a quadratic form on H1 gamma tilde minus such that, and we have 3 conditions. The first one is Q is positive definite. The second one is that Q of L, or let me call it something else, of Z is greater or equal to 0 if Z belongs to H1, greater or equal to 1 if H1 of gamma tilde Z minus. So for the integral elements, you take at least value 1. And finally, the last one is Q of LE is 1 for E belonging in the edges of gamma with L of E different from 0. Yeah, so this is a real quadratic form. Wait a minute. Codimension 1. What?
Strata, because the dual graphs are labeling the strata, right? In the varieties on its way.
Yeah, yes.
So even shouldn't on the codimension 1 strata, shouldn't it always extend? Just because, you know.
No, but it extends if you restrict to the stratum, not if you. I mean that. I mean actually we know, and you'll see. Let me just. You'll see that actually that's a no. I mean so it will not extend. I mean only. Okay, so the perfect, and then. Yeah. Okay, and the central cone is the same as perfect plus an additional condition, which is Q of Z is equal to 1 for all Z in H1 gamma tilde Z minus. So I mean, let me make some remarks to kind of parse this one. So this one basically gives you a complete combinatorial description. If you give me a dual graph, I should be able, using this one, to tell you if it extends or if it doesn't extend. Of course, the obvious thing that you see here is that it's much easier to check extension for Voronoi versus anything else. Because for Voronoi, I'm just checking the determinant of a matrix. So I have natural basis. And for the other ones, I have to find a quadratic form, which there are algorithms, but they are kind of ad hoc. So I can solve it for any given problem, but not kind of like a general situation. The second remark is, of course, I mean, extension to central implies extension to perfect. I mean, of course, this is a stronger condition to extend. And in fact, extension to Voronoi, it implies extension to perfect, and this is a result. This is a corollary of results of Mello-Viviani. Which simply says that because the monodromy cones are generated by rank 1 quadrics, then everything happens in the matroidal locus. You basically deal with matroidal cones, and then basically in that situation, Voronoi implies perfect. So this has to do with the fact, and this is in particular as a corollary, once you know Mello-Viviani, you automatically go from, in the Jacobian case, you automatically get the result that it extends to perfect cone. And finally, you want to get better results. So better results would be to say geometrically. As I said, we have the theorem of Alexeev, Birkenack, and Hulek, which tells us that the indeterminacy of the pre-map to Voronoi is the union of the Friedman-Smith and loci, the closure of this loci. And, okay, so our theorem is that we know that Fs2 union Fs3 is included in the indeterminacy of the perfect cone compactification. We know, of course, this is included in the Voronoi compactification, as I said, so this is the union of all these strata. And we know, furthermore, we know that Fsn, the open stratum, so this is the open stratum, is not included in the indeterminacy of the perfect for n larger than 4. So we know that actually on the open stratum it extends, and kind of conjecturally, I know, and we have like proof in small genus and in high codimension. So conjecturally, the indeterminacy of the perfect map would be the union of these two strata. But at this point, we cannot rule some sort of strange degeneration deep into the boundary of FSN stratum. So for the generic one, we check that, and I mean, so it's a strange behavior that 2 and 3 are special, and then from 4 on, you extend it. And this is actually kind of good for us because we want to extend to cubics, and that's helping us there, but I don't know. And just kind of a final word for the central cone. We have even less results, but there exists degeneracy. There exists some point of indeterminacy. So let me say it this way: the indeterminacy of the period map to the central cone minus the Friedman-Smith locus of the union of FSN bar is not empty for n big enough, for G big enough. So this is kind of making sense in the context of Alexeev-Bruniat. So for the central cone, there are some sort of strange exotic behaviors that start occurring only for high genus, and we have such an example, in some sense generalizing the example of Alexeev and Bruniat. And I think my time is up.